Okay, today we're going to look at net force, and in our last lesson we said the net force is considered like the resultant, or the definition is the net force is the vector sum of all forces acting on the object. So in this case you want to be careful, because if we're dealing with the vectors, we got to worry about directions. So we just have to be clear that we're dealing with vectors, right? So our net force is the vector sum. So we have to be really careful of size and direction. So let's do an easy example. So let's say that we have an object. We'll just draw it as a box like we did before. So we have an object, and let's suppose it's getting pushed forward with 100 newtons. So forward to the right, and we got force of friction going backwards at 20 newtons. So let's say our applied force is 100 and our force of friction is 20. So the idea is, what would the net force be? So we can calculate the net force by just adding, right? We're just doing a vector sum. So we're just adding all of our forces. So we have 100 to the right, so 100 is positive. And we have 20 to the left, so the left is negative, so we'd have 100 plus negative 20, which would give us 80 newtons to the right. Positive 100 minus 20 would be 80, so we could write it as 80 newtons. We could say positive 80 newtons, that would indicate to the right, or we could say 80 newtons east, or use the word right, whatever. They're all the same thing, so it doesn't really matter how you would explain it. Okay? So obviously, if we got forces going in a linear sort of fashion, it's pretty basic. You're just adding and subtracting. So let's add to this question. So let's suppose we got 20 Newton force of friction again. But in this case, we've got one person. So we got an applied force of 80. And let's suppose we have another person. So we have another applied force. Let's call it applied 1 and applied 2 to indicate the two different people. So we'd have, let's suppose the second person pulls it at 60. So in this case, our net force is 60 plus 80 plus negative 20. So that would give us an answer of, we have 140 minus 20 would be 120. So we'd have 120 newtons to the right. So pretty basic questions if they are acting in linear fashion. They're either both up and down or both sideways, whichever the case may be. Where these questions get a little bit tough is when they're not linear and you got some sort of angles involved. So let's suppose we have a box and someone's going to push it north at 80 newtons. So we have some sort of applied force at 80 newtons that way. And let's suppose somebody else is going to push it sideways to the right at 60 newtons. So we'll call that one person 1, that one person 2. So we have 80 newtons and 60 newtons going in vectors. So in this case, we can't just simply add the 80 and 60 because they're not in the same direction. So we have to take care of this in terms of a vector question. So then what you'd want to do is we have to basically draw it just like we did in the last unit. So we have 80 going up, then we draw our second vector tip to tail, so we have 60 to the right. So our answer that we're actually looking for, our net force, will then be the resultant. So just like we did with vector questions in the last chapter, we just have to do simple trig. So our net force will be 80 squared plus 60 squared, and we want to square root that answer. And then we would also calculate the angle, because remember we need the size and the angle, so we'd have to go second tan for that. So our side, 80 squared plus 60 squared, square root that gives us gives us 100. And our angle, if we go 60 divided by 80, second tangent gives us, oops, I messed up, 60 divided by 80 is 37 degrees if we round it off. Okay, so that means in this case our net force will then be just our vector answer. So we'd say 100 newtons at north 37 degrees east. Okay, so just like we did with other vector questions, it's pretty much exactly the same thing. Okay, let's look at another example now that's a little bit more difficult. So let's suppose we have a car that's stuck and we're going to have one person pull on it with a force of, let's suppose they pull on it with 100 newtons at an angle of 20 degrees, and then we have the other person pulling at 120 newtons, but they're pulling at 30 degrees. And let's even add friction in here, so we've got friction going backwards, and the force of friction, let's suppose, is, let's say 40 newtons. So we have friction going backwards, 40 newtons, we've got one applied force. Actually, let's even do tension this time. Let's suppose we're going to tie a rope to the car, and each person's going to pull a rope. So we'd have person one's tension and person two tension. Okay, so there's our setup. So now the question is, what is the net force? What is force net? Okay, so what we want to do with this is, just like we did above, we got to deal with vectors, but we got more than two vectors going on here. We got three, so we're going to have to actually combine all of our vertical and horizontals just like we did before. So first step is we need to calculate each of those. So we want to figure out what the horizontal component is of the two vectors. So we want to figure out the horizontal and the vertical for each of those. So for that first triangle one I just sketched on, we got the blue one, the opposite will be our sine. So we'd have sine 20 equals y over 100. So we can calculate that one. So that works out to 34.2. Then we want to calculate the same thing, but do cosine. So go cosine 20 equals x over 100. And that one is 93.96, so we'll round that one up to 94.0. Okay, so we got our two components for that 100 Newton force. So now what we want to do is the same thing, but we want to do the bottom triangle. So this one's going to have a horizontal component and a vertical component as well, but it'll be going downwards instead of upwards. So we'll do the exact same thing for that part. So you'd find your sine 30 is y over 120. So when we calculate that one, we'll get 60, and then we want to go cos 30 equals x over 120, and that one works out to 103.9. And that's it. So we've got our horizontal and verticals figured out for that, and then we've got our friction. We don't have to do anything with that one because it already is horizontal. It's backwards at 40. So we've got all of our vectors figured out. So now, just like we did before with our last unit, we want to do the same thing. Our net force, we want to figure out our net force in both directions. So our net force horizontally, or in the x direction, let's call it, will be 94.0 plus 103.9 and negative 40. Okay, so we'll add all those. So 94 plus 103.9 and negative 40 gives us 157.9. Okay, so we have 157.9 newtons of force horizontally. So that, because it's positive, it'll go to the right. And then we want to do the exact same thing for the vertical direction. So our F net vertically, or in the y direction, will be 34.2 upwards, and we're going to add negative 60 downwards. And we have no vertical for our friction, so it's just those two. So we add those two, we get negative 25.8 newtons downwards. And that's it. So we've got our components figured out. So let me just erase all of this stuff. So we have everything that we need for our two vectors. So we've added them vertically, we've added them horizontally, we've got our two net forces. So just like we did it before, we want to put these together now as well. So we'd have our y direction, we've got 25.8, so that'll be downwards, 25.8. And then we have a horizontal component of 157.9. So we'll draw that one as sideways to the right. So there's our two net forces. So our final resultant force will be the vector from start to finish, the resultant. So we want to figure out that and that angle. And we're done. So we basically do it exactly like we just did before. Use Pythagorean theorem, 157.9 squared plus 25.8 squared. Square root your answer. And we get 159.99, so we'll round it off to 160. And then we need to calculate our angle as well. So 25.8 divided by 157.9. Second tan, and in this case we get 9.3 degrees. So we'll just round it off to 9 degrees is close enough. So we would say east, 9 degrees south. If we were to actually take that vector and draw it on the diagram, and we kind of drew it accurately, we would see that it would be a little bit below horizontal, and it makes sense because the bottom guy's pulling stronger and a bit bigger of an angle, so it's going to sort of win the tug of war. It would be 9 degrees, so it would be a little bit downwards, and it's 160, so it's going to be somewhere bigger than both of them, right? Because one guy's pulling at 100, the other guy's pulling at 120, so together it would be the same thing as just one person pulling at 160 at a 9 degree angle. So that's it for those. Let's do one more example. And these ones tend to cause people a little bit of trouble, and that's when an object is in equilibrium. So if something's in equilibrium, that just means all forces are balanced. So F net is equal to 0. Okay, balanced forces. Oops, I didn't write that very good. Okay, so we have balanced forces, so everything is balanced out, everything is equal. So that means we have balanced forces horizontally and vertically. And that's the key to doing these questions. You have to make sure that you treat the horizontal and vertical separately. Okay, so let's suppose in this case we've got a sign. So we've got a sign outside of a store, and it's hanging, and what's holding it up is we got a horizontal rope tied to the building, and then we got another rope tied up to the top, and let's suppose it's at 40 degrees. Okay, so we have two ropes holding up this sign, and let's suppose the sign weighs 25 kilograms. Okay, so the first thing we want to do is figure out all of our forces. So we've got gravity pulling this thing straight down, so force of gravity. And in this case, we actually have to calculate the force of gravity. So we're going to learn with Newton's second law that force equals mass times acceleration. But we can start now. So our force of gravity is just going to be the mass times the acceleration of gravity. So quite often we write it as mg. So that would equal the mass, 25 kilograms, times the acceleration of gravity, 9.81. So that means the force of gravity is 245.25 newtons. Okay, so we have our force of gravity pulling downwards. So now the next question is, what are the tensions in the rope? So we want to know tension 1 and tension 2. We want to know what are those two tensions in the rope to hold up that 25 kilogram sign. So we know gravity is going downwards. That's our only other force acting on the object. So that means, in this case, then that force of gravity downwards, if it's 245 going down, that means the vertical component, and out of these two ropes, the only vertical component is that one on the triangle, so that means that one has to be 245.25 as well. And then you can see the only other components we have are these two horizontals. So this one has a horizontal to the right, and this rope is horizontal to the left. And if it's in equilibrium, that means those two things have to be the same. So all we have to do with this one is calculate the tension on each rope. So what I'm going to do is I'm going to actually, because I do the triangle differently, I want to change it. So you can see here, instead of going over and up, I want to draw this upwards. So we know that that's 245.25. And then I'm going to draw my horizontal component from there. So you can see it doesn't matter which way we go, but in this case our 40 degrees is inside the triangle, so that should work. Otherwise, if we were to use the bottom triangle, I would have to use 50 degrees instead. But it'll work whichever way you want. So let's do the calculation for that horizontal component. So we got the 40 degrees, we have opposite, and we want adjacent, so we'd have tan 40 will equal 245.25 divided by x, right, if we're solving for that x side. Okay, so we just got to basically divide those out. So our x will equal 245.45 or 0.25, sorry, divided by 1040. So if you do that on your calculator, we get an answer of 292.27. So we'll just round it off to 292 is close enough. Okay, so that means we have 292 going to the right. So that means the rope to the left also has to be 292 because those have to balance. So you can see we've got one question answered. So we know that tension 1 was 292 newtons. So the only thing we got left to solve for is tension 2. And tension 2 was this angled one. So all we have to do is we've got our two sides of the triangle. The easiest way is just use Pythagorean. So we'd have 245.25 squared plus the 292 squared. And then square root the answer, and we get an answer of 381.5. So we'll round that off to 382. Okay, so we'll have tension 2 equals 382. And we're done the question. So if the question was, what are the two forces? Because we know they're in equilibrium, the sign's just hanging there. The verticals have to be the same, the horizontals have to be the same, but opposite directions to balance out. And we're done. So let's suppose the question was something like this: find the tensions in each rope, and then it says maybe the rope can only withstand a force of 300 newtons. What would be the problem? Well, if it can only withstand 300 newtons, tension 1 would be okay. It's less than 300, but tension 2 is way bigger than 300, so that rope would likely break. So we'd have to use a rope that's a little bit stronger or whatever to do this question. And that's it.